Hello everyone, welcome to a new video in which we'll be discussing questions from previous year questions from EMT. Right. So yeah, so let's start. So electromagnetic theory, PYQs. Okay, let's do one by one. Alright, we will be doing questions and we'll do some standard questions, some real good questions. Okay, so first question, let's write a solid sphere of radius r has a volume charge density has a volume charge density rho is equal to rho naught sine 2 theta. Okay, rho is equal to rho naught sine 2 theta. How does the leading term, how does the leading term, okay, in the electrostatic potential, in the electrostatic, how does the leading term in the electrostatic potential depend on the distance r, depend on the distance r far away from the charged sphere, far away from the charged sphere. Okay, so question options are option A is r is 1 by r, option C is 1 by r square, option D is does not depend on r. Solid sphere radius r has a volume charge density rho is equal to rho naught sine 2 theta. And how does the leading term in the electrostatic potential depend on the distance r far away from the charged sphere? Okay, please try. First try, then we will do it. Solid sphere radius r having volume charge density rho is equal to rho naught sine 2 theta. So it depends on theta. How does the leading term in the electrostatic potential depend on the distance r far away from the charge sphere? So first of all, let's draw a diagram for it. So this is a sphere. Okay, this is a solid sphere. So let me do this. This means solid sphere. Okay, so radius is r. Okay, and the charge density on the solid sphere is rho is equal to rho naught sine 2 theta. Right. So the leading term in the electrostatic potential depend on distance r. So electrostatic potential we have to calculate. Right. So for that we need to really remember the formula. So right only according to multiple expansion. There's a formula for it. Multiple expansion. Into multiple expansion. VR electrostatic potential VR is equal to 1 by 4 pi epsilon naught. Okay, 1 by R rho dV. Okay, 1 by R rho R dash dV plus 1 by R square is volume integral R dash cos theta dash, okay, rho R dash dV, right, and it will go on. So this is the formula. You just have to remember it. I have to remember it. Okay, so first let's calculate this term. Okay, because what is the question? Okay, let's find out this term. Rho R dash dV. Okay, so how to calculate this one? 0 to r is for the r coordinate for the spatial coordinate, 0 to pi for theta, and 0 to 2 pi for phi. Okay, this is for phi, this is for theta, and this is for r, right? So rho r, what is rho naught sine 2 theta? Okay, and what is the this r and this r is different. Okay, that's why I've written r dash. So r dash square, okay, r dash square sine theta, hmm, d r dash d theta d phi, right? So this is the integration we have to do. So rho naught is a constant, it goes out. So what integration is left? 2 pi for phi, phi becomes 2 pi d phi integration. 0 to pi sine theta, okay, there is sine 2 theta, sine theta, all right, we'll do that. Integration 0 to r, r dash square dr dash, and 0 to pi sine 2 theta into sine theta d theta, all right. So let's do one thing. So 2 pi r rho naught, this becomes r cube by 3, right? Yeah, into, okay, let's do this one. 0 to pi sine to theta, I can open sine theta into cos theta, right? Cos theta into sine theta d theta. So if we do it, it's 2 sine square, it becomes 2 sine, is 2 pi rho naught r cube by 3, 2 sine square theta cos theta d theta, all right, 0 to pi. Yeah. So see the integration of this one. If you remember integration for fn x f dash x dx. Alright. So that is f n plus 1 x by n plus 1. If the derivative of this function is there, so the integration will be this one. So 2 pi rho naught r cube by 3. If you see, 2 goes out, so it becomes 4. Sine cube theta divided by 3. Alright, 0 to pi, isn't it? Because the derivative of sine theta is cos theta, and it has a power, so sine cube theta by 3. And the thing is, sine pi is 0, sine 0 is 0, so this whole thing becomes 0. So there is no dependence for this term. Okay, so this whole term becomes 0. So we have to find this term now. Okay, to get the dependence of r. Okay, electrostatic potential dependence on r. So let's calculate this integration. This integration will be integration r dash cos theta. Okay, cos theta. I think it should be dash also. Everything should be dash anyway. R dash cos theta dash rho r dash dv. Right? Because actually not okay. Okay, okay. Uh, okay. Yeah. No, no, no problem. No problem. Okay, so you can write it to theta also. No problem. So this is v. That means the integration for this one will be again v. That means integration 0 to r. Okay, okay, 0 to r, 0 to pi. This is for r. This is for theta, and 0 to 2 pi. This is for phi. Okay, so what should we do? Yeah, rho r dash we haven't put here now. Rho naught sine 2 theta. So we will put rho naught sine 2 theta is there. Okay, so let's do it. Okay, rho naught goes out. Okay, so r dash, okay, r dash cos theta sine 2 theta, then what, r dash square sine theta d theta d r dash d phi, right? So yeah, so this becomes, if we kind of simplify it, to integration of d phi goes 2 pi, okay, 2 pi rho naught, and now what integration is left? 0 to r dash cube dr, 0 to pi, there is sine theta cos theta. Okay, if I do the see, if I multiply 2 and divide by 2, okay, 2 cos theta sine theta also becomes sine 2 theta, so this becomes sine square 2 theta, correct? Sine square 2 theta d theta. Okay, Yeah. So this becomes pi rho naught. If you see a cos term will come, so there will be a dependence. Okay, we will get the dependence term. So this becomes r fourth by 4, right? Into this becomes 1 minus cos 4 theta divided by 2, and integration still there, 0 to pi. Some people do what? They write it and they put the limit. They feel like it is an integration. No. Okay. So see, let's do it now. So there is a term coming for theta, so there will be dependence. It won't become 0, r4 by 4. Integration theta by 2 minus sine 2 theta, sorry, sine 4 theta by 8. Okay, 0 to pi. That is the limit. So this becomes 0, but this still there. So pi rho naught r4 divided by 4 into pi by 2. Alright, pi by 2. Yeah. So mm, this is not 0, right? So this term doesn't become 0 and it is a constant quantity. So if we put it here, where? Here, let's put it here. So VR becomes VR, if you see 1 by r square, it was like this 1 by r square integration r dash cos theta dash, okay, and rho r dash d theta, right? Something like that, alright? Integration, whatever there. So 1 by r square, the whole integration is this much, rho r naught r fourth pi by 8. This is a constant quantity. We need the dependence of potential upon r, which is this. Okay, so V is proportional to inversely proportional to r square. Okay, so this is the answer. It's a very good question. Option C. Just have to remember this multiple expansion. Okay, let me write it again. Formula. So multiple expansion formula for potential. Okay, for electrostatic potential. For electrostatic, okay, expansion electrostatic potential VR, okay, is equal to 1 by r integration 1 by r integration rho r dash dr dash plus 1 by r square, okay, volume integration r dash cos theta dash rho r dash, okay, and this is dv, right? I mistake here. This is dv. Dv means your d theta d phi. Okay, what is dv? In place of dv, what do we write? R square sine theta d theta dr d phi, right? This is the substitution of dv and the triple integrations. For d theta we take 0 to pi, for d phi we take 0 to 2 pi. So this is the volume integration. So this is the formula we have to remember, okay, for this type of question. This is a solid sphere of radius r, has a volume charge density is given. So if the question is asked what is the dependence of electrostatic potential, we have to do it this way. Okay. Next question. Question number 2. An infinitely long cylinder, of radius r has uniform volume charge density, a spherical region of radius r, a spherical region of radius r, okay, is carved out of it. Okay. So at what value of r, what value of r, okay, is the electric field maximum? What value of r electric field is maximum? So infinitely long cylinder, okay, and inside it there is a solid spherical region, okay, radius r, okay, this is an infinite solid cylinder. What value of r electric field is maximum, okay, from the center? So yeah, let's try. Infinitely long cylinder R has uniform volume charge density, so rho will be there. Spherical region of radius R is carved out of it, means drawn out of it. What value of R electric field is maximum? Okay. Option A, R is equal to 3 by 2 R. Option B, R is equal to R. Option C, R is equal to 2 by 3 R. Option D, R is equal to 4 by 3 R. So let's try. So an infinitely long cylinder is there. So suppose charge density, volume charge density, that's why it will be rho. Okay. Assume a sphere of charge density rho. Okay. So suppose there is another charge. There is another. Suppose there is a sphere minus rho inside the cylinder. Right. Suppose assume a sphere. Assume a sphere of charge density. Sphere of charge density minus rho is embedded means put inside the cylinder, right? Right. So field outside electric field outside the long cylinder will be what? Outside the long cylinder at distance r. Okay, electric field outside the long cylinder, the cylinder. Okay, out cylinder. Outside the long cylinder, what is the formula? Cap suppose E1 vector is equal to rho r square capital R square, which is the radius, divided by 2 epsilon naught r cap. Okay. Now E inside, okay, E inside suppose E2 vector is minus rho r square divided by 3 epsilon naught r square r cap. So this is the difference between inside and outside of an electric, like for the cylinder. Outside it is 2 epsilon r, or inside it is 3 epsilon r. Okay, so the total electric field will be E total will be E1 plus E2. Okay, so that will be rho r square by 2 epsilon naught r cap minus rho r square by 3 epsilon naught r square r cap. Right. Okay. Mm, I made a mistake here. There is a r square here. Sorry. All right. Sorry. So now what for maximum minimum? Why I did this? Because I need the for what value of r there is relative field is maximum. So for relative field to maximum, what will happen? dE by dr should be 0, right? For relative field to maximum or minimum. Yeah. So d by dr of rho r square by 2 epsilon naught r square minus rho r. Forget the r cap, 0. Okay. So mm, I'm sorry again. There is no. Just a second. Yeah, I made a mistake again and again. There is R here, and this is R cube. Okay, if you remember the formula, I made a mistake here. Here also, yeah, this is R cube. So inside it is rho R square by, sorry, outside it is rho R square by 2 epsilon naught R. Inside it is minus rho R cube divided by 3 epsilon naught R square. Okay, pardon, my bad. Alright. Otherwise, this will, there's no point of this derivative. Minus rho R cube divided by 3 epsilon naught R square. Okay, so the derivative becomes, so one what rho by epsilon or rho R square by epsilon naught. If I take common, so d by dr of 1 by 2r minus r by 3r, correct? R square is equal to 0. So derivative we have to take, so minus 1 by 2 r square minus 1 plus 3r by, sorry, 2r by 3r cube is equal to 0, correct? The derivative. So minus 1 by 2r square is equal to minus 2r by 3r cube. So minus minus cancelled out. So r square, this is r. So r is equal to 4r by 3. Okay. So yeah, so I think that will be your r is equal to 4r by 3. Yeah. All right. So this is yeah, that's correct. This is correct. So answer is what? Option D, 4r by 3. To get it is again you have to remember formulas for it. E outside is rho r square by 2 epsilon naught r for a cylinder. E inside is minus rho r cube by 3 epsilon naught r. Okay, let's write the formulas for the cylinder. Okay, for an infinite cylinder with volume charge density rho. Okay, so rho out, E outside, E outside is equal to rho r square by 2 epsilon naught r cap. E inside is minus rho r cube divided by 3 epsilon r square r cap. These two formula we have to remember. Just write it down. Alright. So yeah, let's move ahead. Next question. Question number 3. Let's move to question number 3. Okay. I had a question. A conduct. Okay. Just wait. Anyway, I know. A conducting sphere of radius r. Conducting sphere of radius r. Radius r is placed in a uniform electric field. It's placed in a uniform electric field E. Okay. It will be E naught. Sorry, E naught directed along z axis. E naught directed along z axis. Okay. Yeah. So potential for outside points is given by potential for outside points. Potential for outside points is given by sorry, V is equal to V V out is equal to E naught 1 by R whole cube, capital R divided by small r whole cube, cos theta. Okay, cos theta, R cos theta, sorry, R cos theta. Okay, so where R is the pattern, where R is the distance from the center, where R is the distance from the R is the distance from the center, and theta is the polar angle. Theta is the polar angle. Okay. So charge density on the surface of the sphere is. So charge density is asked here in this question. The charge density, the charge density on the surface of the sphere is on the surface of the on the surface of the sphere is alright. So what are the options? Option A 3 epsilon naught E naught cos theta. Option B epsilon naught E naught cos theta. Option C minus 3 epsilon naught E naught cos theta. And option D 1 by 3 epsilon naught E naught cos theta. So this is the question. Here conducting sphere is there. Radius r, uniform electric field E naught along z axis. Potential is given. So charge density on the sphere. First of all, if potential is given, how to calculate electric field? E is equal to what? Grad V, gradient of V, right? Or here, what? Minus del V by del R, right? So, because the answer is in cos, if you see the option is in cos theta. Okay, that means from here we can take a hint that this potential won't be varying with theta, right? It will be varying with r, right? Because there is no r here, so eventually r got cancelled somewhere, and theta remains. Like cos theta has remained, yeah. So we don't have to take the theta component, but theta component is not there, na? Yeah, minus del by del r will be the answer, yeah, like the electric field. Okay, yeah. So first of all, um, this is a conducting sphere. Okay, solid, no, not solid. Conducting sphere of radius r. Right? So first of all, for conducting sphere of radius r, for a conducting sphere, what is the electric field inside? For a conducting sphere, electric field inside is zero. This is a conducting sphere, radius r. So for a conducting sphere, this is a conducting sphere. So electric field inside is zero. First of all, only electric field exists outside. So there will be electric field outside only. And what is the formula for electric field outside? It is sigma by epsilon naught. Okay, at r is equal to r. Whatever. Outside or on the sphere. Okay, on the sphere also sigma by epsilon naught. Yeah. So if we do so e out, we can like we need this sigma, right? It's asked in the question. We need the charge density on the sphere surface of the sphere. So on the surface of the sphere, sigma by epsilon naught. We can say e out, not outside, but e surface. We need on the surface now. So yeah, e surface is sigma by epsilon naught. So e is equal to minus del v by del r, correct? So minus del v by del r of, and we can equate it to this, and we will get the expression for sigma. So del v by del r. So v is given this much. V out means same. So on the surface, this one. Okay. So E naught 1 minus r by r whole cube call r cos theta. So this is the expression for v. Okay. Yeah. Correct. Yes. So let's take the derivative. Let's take all the constants out. Minus E naught cos theta also get out because the dependency is on R. So del by del r of 1 minus, let's take R inside. R minus, okay, RQ by R square. Yes. Now it is simplified. Why to complicate things? Minus E naught cos theta. Now the derivative 1 minus, this becomes 2RQ by RQ, and this becomes plus, right? Correct? Got it? Yeah, the derivative. 1 by R square derivative is minus 2 by RQ. So this is your E, right? E surface or E outside, whatever you can say. So we will equate it to our sigma by epsilon. Correct? Sigma epsilon naught is equal to minus E naught cos theta and 1 plus 2RQ by RQ. Okay, now the thing is, it is on the surface, like this electric field is on the surface. So on the surface, r is equal to r, the distance is equal to radius. So we'll put here, so sigma by epsilon naught is equal to minus E naught cos theta. Okay, 1 plus 2, this is becomes like 1, right? So 1 plus 2 is 3. So sigma is equal to minus 3 epsilon naught E naught cos theta. So that will be 1. This is the required surface charge density, which will be option C. Okay. Again, a very good question from okay. Very good question again. Standard question. So you should be able to solve it. You should be solving it because not everyone will be able to solve it. So you should be able to solve it because how can you crack an entrance exam? It depends on how unique you are, like how unique questions you have done. Because if everyone has done that question and you have also done that question, it doesn't make any difference. So how different questions you have done from others, that will decide your qualification and also rank, right? So you have to do these tough questions. You cannot leave tough questions every time. You have to do it. All right. So this is your question number 3, right? EMT is a very good paper. It's a very interesting paper if you do it properly, if you understand it. Otherwise, sometimes it becomes tricky. But if you understand it, it will be very, you'll enjoy it. And that's the thing. Okay. Okay. So is it done? Should we move forward? Should we go forward? Yeah. Yeah. Okay. Write down a long cylindrical wire. Next question. Question number 4. Question number 4. A long cylindrical wire. Long cylindrical wire of radius r and conductivity sigma. Of radius r, of radius capital R, okay, and conductivity sigma. Conductivity sigma. Lying along the z-axis. Lying along the z-axis. Carries a uniform axial current density. Carries a uniform axial current density. Uniform axial current density J. Okay, current density J. The pointing vector on the surface of the wire. The pointing vector on the surface of the wire. The surface of the wire is what? Okay. So option A, J square R. J square R divided by 2 sigma rho cap. Rho cap means which coordinate? Cylindrical coordinates. J square R by 2 sigma rho cap. Option C. Option C. J square pi R divided by 4 rho, sorry, 4 sigma phi cap. And option D, J square pi R by 4 sigma 4 sigma phi cap. This is a minus one. Okay. This is the cylinder here. This is R. This is along Z cap. This is a J. Okay. Lying along the Z axis carrying a uniform axial current density. The current density is along the axis. So axial current density. So current density is along Z axis. Okay. So we can write J is equal to J Z cap. You have to find pointing vector on the surface of the wire. So pointing vector means what? Pointing vector we know. Try this question. You have to find electric field and magnetic field to get pointing vector, right? Pointing vector S is equal to E cross B by mu naught or E cross H. Yeah. So now you have to find electric field for the wire. So we know from Ohm's law, the vector form of Ohm's law. If you remember, J is equal to sigma E, right? J is equal to sigma, so E vector is equal to J by sigma. Very easy. And J is along Z cap, so electric field will also be along Z cap, right? So J by sigma Z cap, right? Now magnetic field because of a wire. Okay, now J is equal to what? Okay, current is equal to J dot A, right? Current is equal to J dot A. So current density, yeah, current is equal to J dot A or J A simply. Okay, so mu naught I by, for a cylindrical wire, 2 pi r, yeah, and this one magnetic field will be along phi cap. Magnetic field will be along phi cap. So I is your Ja. So mu naught Ja divided by 2 pi r phi cap. Alright. So now let's do one thing. Uh, okay. J pi A, what is area? Area is pi r square. So mu naught J pi r square divided by 2 pi r. So pi pi cancelled out. R got 1 cancelled out. So mu naught J r divided by 2 phi cap. Right. So let's do the pointing vector now. S pointing vector S vector is equal to E cross B divided by mu naught. So E is your J by sigma J Z cap by sigma cross mu naught J r divided by 2 phi cap. We all have studied Ohm's law, but it needs to click at that very moment. Like at that moment, it needs to click that the electric field can be J by sigma. Okay, sometimes it doesn't click in exams. So mu naught cancelled out. So this is Z cross phi is how much? See, what is the cylindrical quantity? Rho phi z, right? So rho cross phi is z, phi cross z is rho. So z cross phi will be minus rho, correct? So minus rho cap, and this is j square r by 2 sigma. Yeah. So the answer will be minus j square r by 2 sigma rho cap. Okay. Which option is it? Option B. Is it correct? Minus j square r by 2 sigma rho cap. All right. Yeah. Rho cap or r cap, anything. R5Z or rho 5Z, anything. Okay. Yeah. Again, a good question. Right. Okay. So yeah. So that will be it for this class. We'll be solving more questions in the upcoming sessions. All right. Yeah. So please keep your like keep on your studies and let me know anything, any doubts in the comment section. All right. Yeah. Thank you.